Alrighty. So happy Tuesday. We are keeping warm here in the classroom at least. So we're going to talk about exceptions and pointers and Project Zero. It's a little bit of a blitz today. Unfortunately, I won't be able to make it Thursday for lecture. I've got to do a follow-up with the surgeon, and that was the only time he had available for like 4 weeks. And he's like, well, you got to see me soon. So I won't be able to make it Thursday. I might be able to post a video or something for you guys if you want some additional stuff. I can do that. I just won't be able to be here live. So maybe I'll just post a recording in Canvas for you for Thursday, because I don't know if we'll get through everything today that we want to. Although we should be able to get decently far. So exceptions are going to be the way that we communicate with code that calls our code that uses our code, right? We don't want our classes to just print out errors. That's not helpful. People are just going to ignore them. One of the ideas with our object-oriented programming is we've encapsulated all the details of our class into one nice, neat little package, and we're protecting the integrity of our class. If you try and do something that's not allowed, we're going to tell you. Right? And the way to communicate that is with exceptions. So we'll have to handle those. And then we'll start talking about pointers. We're going to use pointers for our project. We can do lots of things with pointers here. It starts to get pretty interesting once we start using pointers. This is most everybody's least favorite topic in C++, which is unfortunate. It's important that we do it right, and this will help us avoid bad things happening. So I'll show you, I told you I was going to try and crash my computer. It shouldn't actually crash with a memory leak, but it'll just start eating up all the memory and things will slow down, and hopefully don't break anything. It should be fun, so we'll do that. And then next week, we'll get into arrays and vectors. You should have done these already from CIS 150. We'll spend a little bit more time. We'll get into two-dimensional arrays and vectors because those are much more interesting. Spend some time with that. As one of our projects, we'll use 2D vectors or arrays if you like arrays. I just like vectors because they're easier. Shoot. That's going to beep at me the whole time. I'm sorry. I ran out of insulin because I'm stupid and didn't check this morning. Just trying not to freeze this morning before I got here. So that's what we got planned for today. And then we got lab tonight. We'll do classes and exceptions. And then probably the lab on the 28th will work on pointers specifically, because we got into a little bit with our classes. We'll bring in the exceptions tonight for our lab, and then we'll save pointers for the lab on the 28th as we go from there, okay? All right, awesome. So let me fire up Visual Studio here, and I'll do a new project. Don't need these ones. Probably don't need my email either, right? All right, so we do a new project. Again, I'm going to put it in my repository folder here. So here's week 3. This will be exceptions and pointers. I can't spell, that's okay. You don't mind if it's spelled wrong, right? All right. Don't need super large here, right? How's that look? And then using namespace standard because we're lazy. Okay, we have our little cout. Now, we spent some time last week writing classes, and actually kind of want to start there with the exceptions because I think that'll make life a little easier here. So let me go and open that one. Go close this one down for a minute. And we'll come back to this one. So we'll look at our classes we wrote here. So we had our chair class, right? We said, okay, well, what happens if you try and give me a bad height? Well, what do we want to do? Well, now this is our exceptions, right? So if you try and give me an invalid height, the options we had were I could return like a true or false, yes, this worked, or no, it didn't work. But it doesn't make them do anything. If they tell me, hey, your height's -10, and they return false, well, okay, sure, they could just ignore it, right? So being more forceful is using an exception, making them handle it or crash. Right? We've ran into exceptions before. Do we have our main over here, right? I didn't ask for any input, did it? Shoot. Where if you are trying to get some input and you give it something it doesn't expect, it crashes. Right? We deal with those. So what we want to do then is throw an exception here. So our else case, if this is not valid, here we can throw an exception. So we're going to say we want to throw, this is an invalid argument or something. What is it? Exception, invalid argument. So we're going to throw an invalid argument exception, and then you can even give it a message, I think, if we do it right. I need new, I should have looked it up here. Throw new, invalid argument. No. Oh, goodness. All right, we'll go to the Zybooks. That's fine. I can't remember. We'll go look it up. Our exceptions. What's the syntax here? Throwing exceptions. What's the keyword? Just throw. Isn't that what I did? Throw, invalid argument, height can't be negative. Okay. Maybe I didn't have the message before, or I was just confused because those red lines are annoying. So we're just going to throw that exception. So this means when I try and make my chair, it's just going to crash on me here. So classes should throw exceptions. If you throw an exception, it's not your job to handle it, right? It's the code that called your code. So whoever called the set height in centimeters function needs to handle this exception with the try and catch block we're going to look at. So back over here, when we try and make a chair with like -50, and we give this a run, it's going to crash on me here. Did I run the wrong one? There's my exception. Did it not run? I didn't call set height, did I? Nope. I just took it here. I didn't actually call the set height function. So this one probably we want to call set height then. So we'll call set height to the height in centimeters. Now we get our error checking, right? I don't have to do that twice. Now we should crash. Hey, look at that. We get an unhandled exception, invalid argument at memory location. This is not super helpful here, but we can see, hey, it comes in this call stack. Hey, you were at line 10 of main here, you went to your constructor here, and then this constructor called your set chair height here. This is where you're crashing here, and the height you're trying to give it is -50. That's where it's crashing. So we can see as we're running it, here it's crashing on us, and we get this in debug mode. If we just go and run our executable, we'd see it fail as well. We'd actually get that error message like in the output instead of it just pausing our program. Now, it's a little bit ugly to have our else check down here and have the if over here. Again, we're gonna try and be efficient here. So what I really want is if it's less than or equal to 0 here, or I guess maybe just less than, we'll make it negative here. We'll throw our exception. And then what I can do is just have my next code. I don't even need an else block, because if you get to throwing an exception, your code stops. It doesn't run any further. So now we've saved 3 lines of code, we saved an else, we saved some curly braces, and we feel good about ourselves. Some of you might be tempted to even get rid of these curly braces. Please don't do that, right? Technically it's fine, it's just terrible, terrible practice to not have those curly braces there. Some people like it, and if you get out of the workplace and they say, don't put your curly braces around single lines, just smile and nod, but just know it's terrible. Years ago when I was younger, this caused an issue in Safari, and it broke the SSL encryption for websites because one of their devs didn't do curly braces. So I think they're just good. I like curly braces. And if you don't like curly braces, just go write Python. You don't have to use them at all. So let's say, okay, if it's bad, crash or handle it here, and over here we'll go and do something. So if our code that's calling this code knows it could crash, then we need to try and handle it here. So this sort of input's a little bit silly here. So maybe we'll go and ask them for some more information here. So maybe we'll have, we'll see out, enter the height for Eric's chair and an end line, and then we'll have an int for height. We should probably say in centimeters, right? That's lowercase, isn't it? Height. And then we can see in the height. And we'll try and set the height. We'll take Eric's chair dot set height in centimeters, given the height. And if I know this could crash, I want to make sure that it doesn't crash my program, because nothing annoys your users more than crashing. I don't know how many times apps on my phone crash and I just get pissed off at the developers. Like, you should do better, right? Just don't crash, right? It irritates people. So to avoid that, we use the try block. We say, hey, I want to try something that might crash here, that might have an exception. So something exceptional might happen here. So we say, I'm going to try it. And then you can have any other code you want in that try block here. And then what we do is we add a catch block. We say, hey, I want to catch something. So I want to catch an invalid argument here. We'll just call it the exception here, or EX or something here. Sure, I can just see out the exception if it happens here. It's not the most interesting. Exception 2? No, what is it? Exception. There's a way to get the message out. What is it here? Exception dot. Why is it not showing me here? That's all right. Maybe we've got it in here. Where's our try catch? Handling exceptions. Does it print it out here? I don't remember. Really don't remember. Try catch. Okay. Yeah, it doesn't even do anything with it. That's obnoxious. Should have had a better, yeah, there's an invalid argument. Yeah, okay, they never do anything with it. I thought there was a way to output plus output exception. Let's just Google it, see if we have any luck here. What does this one have? Derived class. The throw exceptions with variable error messages. That's what we wanted is handling. Think this one's any good? That's the error message. You don't want that one. That's gross. No. ToString, the stream of that. Oh, man. None of these any good? There might not be a good way to do it then. That's just the catch. Oh, e dot what? Okay, I thought there was an e. E dot what? Do we not have a dot what? Why was it not showing before? It was showing. Guys, I'm just dumb. I'm sorry. It's been a long day already. E dot what, or exception dot what, whatever we want to call this here, right, will give us that exception message here, which is nice. And really we can say, hey, this is a reference as well, if you want to be fancy. And you can even say it's a constant reference. We're not going to change it. It's not going to hurt anything one way or the other. But we're going to try it. And if it's bad, go and do something, right? Hey, you entered a bad height here. Now, if we want the user to actually enter the height, just trying and catching means the code's going to keep on going after this. So the catch block just says, don't crash, do this instead, and then keep going. So what we really need to do is some sort of loop in here to keep this going. Now, some people like these loops and they say while true here. I'm not particularly fond of these. And then in here they'll say break, like, hey, it worked, break out of the loop. I don't particularly like that, but it works. Otherwise, you have to have some sort of variable like successfully set the height, and it starts off as false, and while you've not successfully set the height, and that does seem a little silly to go through a lot of extra work here. So, it's okay. But it'll just keep on going, saying, oh, it was no good, enter the height, oh, no good, keep on going, no good, keep on going, until we eventually get to the break. Because if an exception happens, the code stops running, jumps to the catch. So, okay, something bad happened, let's go catch it and handle it from here. So we can give this a run, and hopefully now we can see, hey, if I say -50 for a height, height can't be negative. That was the error message we gave it here in chair. That's the what you're spitting back out here is that message when we throw it here. So if I give it something valid, here's my output here, like 50 positive, it finishes. Right? We're able to get out of this because we broke our while loop here and we kept on going. So this forces the person who's using your code to make sure that they're dealing with good values here. Particularly important when you talk with users or have users input something because they give you the dumbest stuff sometimes, right? We're like, oh, give me the height in centimeters, and they give you a negative number, or they give you like 10. You know, they type in 10. Well, it didn't even work here at that point, right? Like, that was bad. We didn't even catch that because we only catched the invalid argument exception. We didn't catch the invalid conversions. We had some other ones in here. What were they? There's other error messages here, right? Lots of other ones, common exceptions we can run into. You can make custom exceptions. I never found it super exciting. I like invalid arguments. Pretty helpful, takes care of most of them for us here. But we're going to try and catch. So the class code has the throw if you do something bad. Right? I can't set this attribute to this value. It's invalid based on what's true for my class here. Right? Whatever we've defined for our code, this is invalid. I'm going to throw an exception. Make whoever tried to make it that value do something about it. Right? Returning a true or false could work sometimes here, but it's not as forceful. Right? Using exception forces them to handle it or crash the program. So it lets them do that. And then we can set up, if we're using user input, we just have these loops, right? As long as it's not good, let's just keep on going. These sorts of things here. So we should be able to keep going and keep going and keep going. So other fun things. Did you go through this chapter at all in 150? I think one person said they went through every chapter. And most people are like, no, we skipped around a bunch. Usually we skip around a bunch here. So we're catching, yep, that one's fine. Throwing exceptions. We did our throw. Catch runtime errors, sure. So this one's looking for if values are bad. Now, this is not super helpful to have all that in your try block and then catch it down here. right? Because it's in the same code. I think this sort of putting your try and catches in the code itself here, it doesn't really add any value. Right? You can just check this inside your code. Where we really get the value from exceptions is when classes call other classes, or code calls other classes. When we build it into libraries and things are bad, then we get to deal with it. Right? When you try and get an invalid index out of a vector, we get errors, it crashes on us. That's actually helpful because you know you couldn't get that memory location, right? Versus an array, those sorts of things. The other thing we can do, because there are more kinds of exceptions, is you can have more than one catch block. So the first one we caught was our invalid argument. Then we could also catch these runtime errors here. So you can have more than one catch. You can be from most specific to least specific, because you can have this hierarchy of exceptions. But for ours, we'll do our runtime error, and then we'll see out what again. And hopefully now this works with our, I think this will catch the 10. No, what kind of error is that one? Where it's not catching it here. Goodness, seeing the height. Is it just getting a 0? I don't even remember what this one's doing here. Let's put it in debug mode. We'll try and get a height here off an invalid height. So 10. So height, oh, it just never gets set. Okay, we don't even get that exception trying to get it here. So if we're trying to convert, I think it would crash on us here. So we just get nothing because CN's fun like that. So that's not very useful, right? Where we get our 0, but sure, we did. All right, so we have runtime errors. That one's fine. More examples of that. When we're dealing with file input and output, did you do files in 150? Work with like a basic text file? Okay, good. We'll spend some more time doing files. Where do we get to files? We do our streams, right? Isn't it in here? This is, do we not do streams? Maybe we don't. Okay. I guess if you did 150, that's good. But you get other sort of errors when we're dealing with files we might want the try blocks for. Right, so you can catch, hey, there's some sort of failure in my I/O operations. That's a nice common place for our try blocks as well. All right, and then user-defined exceptions. If you want to make your own, again, you can. You can make your own types of exceptions. It uses inheritance, which hopefully I talked about briefly in 150. We'll get into deeper as we go. That's going to be coming up here. We don't get to that until week 5. We'll do inheritance in week 5. The order here is a little funky, I'm sorry. But you can make one that is an exception, which is a type of exception if you want. Again, if you want custom exceptions, go for it. Most of the time, we're probably fine without them here. So that's not super interesting. So, all right. Our number format, there we go. Our number format exception tries to make it crash here. That's what we wanted to do, right? Where you have to try and catch it. All right. That was not very fun. You guys look bored, I'm sorry. But they're very useful. Right? And we'll practice this in lab tonight. We'll make our class raise exceptions or throw exceptions when bad stuff happens. Right? Get a little practice in. That way we can go and deal with it somewhere else, right? All right, the next thing we want to do is have lots of fun with pointers here. There's a lot to do with pointers. Did you do these at all in 150? One, yes. We really got to figure that out here so that everybody does the same stuff. Makes it much harder in 200, but that's okay. So the whole idea, let me go back to that other project now. So let me close this one down and open up week 3 for pointers. I'll go commit this before I forget. 200. Here was exceptions. All right, and again, it gets cool because you can see, hey, these lines of code changed, right? This one was removed, this one was added at the line level. So you can see how your file evolves in Git, which is fantastic. All right, so we'll go back here. We've got our project. So when we deal with pointers, the whole idea of a pointer is the value that it stores is a memory location. It points to something else. Which seems a little silly, right? When we like declare integers and I say, hey, I have an int for number, it's 42. Number is my name for where this 42 is being stored in memory, right? When I use number, when C++ is running, it's going to go, hey, if I want to see out my number here, it's going to go look up and line, there we go. It's going to go look up what's stored at that memory location. Right, so wherever this is, it's going to go store it. So I've got my variable for number, then I'm storing information. seems like pointers don't do a whole lot more than that, but we can do some silly things with them. So I can make a integer, and we use a star for the pointer called number. What is it warning me about here? Thank you. The little light bulb is helpful. If your pointers don't have a value to start with, right? I don't have a number to point at to start. I should call this another number, sorry. Another number. The good practice to do is to start them at null pointer. So null pointer is just a special value, meaning it's empty. If it's pointed at null, it's not looking at anything. That's our special value we use everywhere. So we can check to see, does my pointer have a value? Is it null or not? So we can look for those sorts of things. Then what we get to make pointers do is we get to point them at memory addresses. So the value of a pointer is the memory address that it's looking at, not the actual value stored in memory. The silly thing is that value has to be stored in memory somewhere too. It's this whole little cycle there. We don't worry too much about that. So I've got my another number here. Then I want to give it the value of something. I want to say, okay, hey, you need to have the value here. So I want to use the value of number. And what I really want is its memory address. So right now it's yelling at me and saying, you can't assign an int to a type of int star. Right? You can't take this integer value and assign it to a pointer. It points to an integer, but it doesn't store an integer. Right? The value that it stores is a memory address. So we have another special operator. We have the ampersand sign. These mean the address of something. So the ampersand is the address of this variable. Where does this variable live in memory now? So I can take, hey, store the value of this memory address for number. And then when I go look up another number, I'll say, what value are you storing? What value are you pointed at? I can go get out the 42 out of memory here. Very roundabout way of going about it here, but that's okay. So we've got number. Then to get the particular value out of cout another number, if I just cout it here, I'm going to get the memory address because that's the value it stores. Right? So when I run this, I'm going to get hot garbage here. 0000299, whatever. This is the memory address of where 42 is being stored in memory. So we don't just out those values here because we get the memory address. Right? This just outputs. Right. Address being stored. So if you want the value that it's pointed at, we have to go and dereference it, which is another fun technical term here. So we'll say, hey, I want another number, and I want the dereferenced value of that. Again, we use that star notation. We say, hey, take the thing that it's actually pointed at, because I know this thing is a pointer. So the star has a lot of different purposes here. So it indicates it's a pointing at an integer, and then in this case, it's saying, actually go look at the thing that you're pointed at. Give me the value that you're pointed at here. This will give you it's the value pointer is pointed at. Here. So now I should be able to get the integer value back out here from that, which is nice. The other thing we get to do with pointers here then, so I can say I want another number. I want to take the dereferenced value of another number and I want to add 1 to it here. Right? So take the value that it's pointed at and manipulate the value it's pointed at here. So now when I print out the number, I should get +1. Uh-oh. I forgot my order of operations here. Yeah, here we go. Possibly incorrect order of operations. Thanks, Visual Studio. This one has a lower priority than the ++. So what I've actually done is said, take that memory address and add something to it, then go see what integer's there. And because there's not an actual integer there, I get garbage, right, out of memory. So one more set of parentheses here will force, hey, get that value being stored here, and then add 1 to it. Now we get 43, which is fun. Right? And then the other thing, because we're pointed at number, if I cout number again, number is going to have changed. Because I changed the value being stored at number's location. Number has that value in memory somewhere. And I said, go change that value. So you can point at another value. So now the pointer references the same value as number, right? And I can go change number. I can say, hey, number equals 77. And we go see out these ones here, the dereference value and the number value. They're going to match, right? Because we've changed what's stored in memory. That assignment operator says, hey, go change the value being stored wherever you're being stored in memory. And every time we run this, we're going to get a different address here. Right now it's F8D4, and I run it again, and I get, now it's FA34, and I run it again, and I get FB84, whatever it happens to be, right? C++ says, hey, operating system, give me a place to store an integer. I need, is it 8 bits, 8 bytes, 4 bytes? Wow, it's not the kind of thing I remember. That's okay. Some number of bytes of memory here, great. And your operating system says, sure, here you go, have it, right? It deals with the memory management. C++ just has to go ask for it here. So we can use pointers to reference the address of where something's stored in memory. Doesn't seem very useful. I know, I get it. It's okay.
So the star is the reference?
Yeah, the star says you're a pointer here, and the star here says dereference. So give me the thing you're pointed at.
Right.
Yep. So we can use those here. The next thing we get to do is we get to finally do some interesting stuff on our computer and use a different portion of memory. So at this point, when everything runs, everything's being run in the stack. So our operating system keeps things for quick reference in the stack. Here, right, we looked at that call stack when the program crashed. It was this one and this one and this one. There's only so much room in the stack. So what we want to do eventually is get to the other location of the operating system. That's the heap of memory. That's everything else here. I don't know how it decides. You can ask the Windows folks or go ask your operating systems teacher later how the operating system decides what's stack and what's heap. But it does that for us. So by using our pointer here, we can start getting at storing things in the heap, which is nice because we're going to have more space for things when we do more interesting manipulations here as we go. Let's see, so this is that's our arrays. Those ones are boring here. So this is dynamically allocated when we go and do this. So what we get to do is use this new operator, and it'll dynamically allocate the memory at runtime based on, hey, operating system, go allocate some space for me here. So we can use that new keyword. And then what we can do, before when you used arrays, you had to tell it what size it was. Right? We said, hey, I have got an int array of numbers. We said, hey, this was like 5 numbers, right? No, int number, am I backwards? I hate C++. I've got 5 integers here, right? But what we couldn't do is get some sort of input here, right? We couldn't say, I want out to the number of numbers to end. I don't know, some nonsense here, right? Oh, that should be full quotes. All right, and then we can have like int for number equals something and cn number. Oh, geez, I already have number.
Numbers.
Values, number of values, sure. Number of values, and then cn the number of values. Number of values. So what you couldn't do is say, hey, I want an array of size number of values. And it's like, oh, it can't be used because it's not a constant. When the program's compiled, it doesn't know how much memory it needs. It's unhappy. C++ gets cranky, so we can't do that, right? So this one is no good here. If we use dynamic memory and use pointers, we can have it allocate at runtime, where it doesn't know ahead of time, hey, is the user going to type in 5 or the user going to type in 7,000? It doesn't know how much space it's going to need. So we can say, hey, I have an integer pointer called my values equals a new, so this new keyword is what we're using here. This means we're going to allocate new memory, an integer array of size number of values. This creates a dynamic array of integers. Now we still use it the same way. So values at index 0, we can assign something here. Values at index 1, we can assign something else, assuming we have a valid index here, right? Like if they tell me 0 items, this is going to go badly. But this is probably fine for now, right? We'll see how well this works for us. 2 is 30. That's probably fine for now, right? We'll assign a couple. So when it goes and runs, enter the number of values to enter, 5 values. Oh, we didn't actually have anything there, sorry. That one's Boring. Oh, it's warning us. We might do a bad thing. We might overload because we don't know what size it is here. We should probably loop off the number of values here, right? This is probably a little bad here. So maybe we'll say for integer index is equal to 0. Index is less than number of values, index plus plus, and we'll take our values at the index and assign it the value of something here, right? I don't know what we want to give. Should we ask them? See how? Enter a value number, and then the index and an end line. And then maybe we have an int for the value, and we see in the value, and then we assign it the value. Sure. We can go do that. Right. Now to get all the values back out, we've got a little bit of problem here, but we can do that. So we're going to say for int index is 0, index is less than, well, I have number of values, no, this is my values, right? Well, values is that dynamic array, but I don't have a good way to get the length of it here, so I still need this number of values, right? Oh goodness, just the number of values. Index plus plus, and we're just going to see out the values at the index and an end line. So we'll get some values in, we'll spit them back out here, and see how it goes for us. And now let's actually see if we can make it go badly for fun. So 5 numbers, I don't know, 10, 20, 30, 40, and 50. 10, 20, 30, 40, 50, garbage. Right? We said, hey, give me a value at an invalid index, and it didn't crash. We went up to the number of values. Remember, there's nothing at that index, right? The length of our array shouldn't have anything there. We did a bad thing, right? And it even warns us as reading invalid value. How nice is that? Visual Studio has gotten really smart here. So now when we fix our less than or equal to sign, we shouldn't get hot garbage again. So 10, 20, 30, 40, and 50. We get our values back out. Life is happier. Right? We did it well, and it's not warning us now we did a bad thing. So, but now we can make an array that's allocated on the heap, which is cool. So now we have more space to do this. So we got number of values here. So let me run this in debug mode for a second and show you. So over here in Visual Studio, you've got some really cool tools that we don't really spend a lot of time looking at, but they're really fun. So this is showing me how much memory is being used by my program right now. So about 788 kilobytes. It's actually a lot of memory being used for not doing a whole lot of stuff, but that's okay, right? This memory is pretty cheap. So when we go and create this array here, it's going to allocate more memory. We're going to see that jump real quick. So if I do a really big number, like a million, that might be 10 million, whatever here. Now we see my memory jumped. Now I'm using 421 megabytes of memory because I have whatever, was that 10 million did I enter? I should have counted. There's 100 million, right? 100 million times 4 bytes per integer. That sounds about right, for 421 megabytes now. So my program is using that much memory because we just told the operating system, hey, I need a place to store 100 million integers. Please give me a chunk of memory. And the operating system says, sure, here's 421 mega memory, essentially. Here's your space. Right? And we can go through, now we're not going to enter 100 million values, because that's going to be terrible here, right? 1, 2, 3, 4, 5, on and on and on. That's not very helpful here, but that's okay, right? Excuse me. So we created that array here. Now, because we're using dynamic memory, we have to do something with it. Right? When I'm done with this memory and my program has other things to do, I need to free that memory up. Because we dynamically allocated it, we have to dynamically deallocate it and say, hey, operating system, I'm done with that chunk of memory, you can have it back. Right? Yeah.
So what happens if you don't do it dynamically? Does it stay in the memory?
Well, remember, we can't make something based off of a user input value without this. I can't make an array of size n where the user enters the n.
Right.
So we can't do it dynamically at all. So when we're done, we're going to use this delete keyword. We're going to delete my values. And then here, I think we add a star. No, delete values, square braces to say, hey, delete the array? Goodness. All right, I got to go look it up here again. I thought I could do this off of memory, and turns out I can't. That's okay. Shouldn't have to memorize stuff. Deleting the array. Delete, then square braces, because of course that makes sense. Why not? Delete values. this will go free the memory up here. So if I have another cout, enter something and cin, I don't know, value, sure. Number, how about cin number? Why not? Right, now when we're running our program, we're going to go allocate a bunch of space here. 100 million. We see my memory should jump here. Right, jumped up to 421 megabytes. Oh goodness, I don't want to enter all those values here. And let's not do these ones here for a second. And we don't need to actually print them out either. Let me comment that out for a second, and then comment these out for a second. Right. I wanted to show this one running. Right. So 100 million. Great, we got a big chunk of memory being used. Oh, I deleted it first. It was only used for a second, and then we deleted it, and it's freed back up. Now we're back to 420, whatever. It was 421. Yeah, now we're back down to our smaller amount of memory. Right? I should have done this one first. Here, let's do it up here, and then one more time. We'll do it twice so you can see it. It's very exciting, I promise. All right, so 100 million. Our memory jumps. We're holding on to that. Right? It's still being used. Our program is waiting for us to enter this first something here. So I enter 10 or whatever it happens to be, and then we call delete, and we freed up that memory. We gave it back to the operating system. So my process isn't holding on to it anymore. So this is where I'm saying you can shoot yourself in the foot with C++. If we do this and don't delete, bad things happen, right? So if I don't delete this value, this values array here, if we just go and make a bunch of these here, so we'll say, I don't know, for int times is 0, times is less than, let's do like 100 times plus plus. If we do all of this 100 times here and never let it go, we're going to have allocated and asked for 100 times that size of memory here. Let's do a cin here. So cin number for a second. I'm doing it the wrong direction. Shoot. Cin that way. Goodness. Wow. Thank you, C++, Visual Studio. All right. So we'll see it jump each time here. Oops, build errors. No, what do we do wrong here? Delete values. Oh, because we didn't declare values. Okay, so it's not letting me delete it because it's not in scope, right? If you create it inside the set of curly braces, it only exists inside that set of curly braces. So we'll just pause on that for a second. We'll come back to that. So we'll see here. So 100 million is waiting for me to enter something. It's jumping up again. Now I'm at 421, 842, 1.2 gigabytes, 1.6 gig, 2.1 gig. It's jumping up and up and up. And if I check my task manager here, I can see, hey, it's eating a lot of memory here. Where's my memory here? My exceptions and pointers here, right? 93% of my system's memory is being used right now. So let's keep on going. See if we can, those are just rookie numbers, right? Can we do better? 94%, 96%. It's eating more and more and more. So it's removing memory from some other things here. At some point, if we keep going, I think it's going to stop. I don't think it'll crash my computer. Yeah, so it puked on us, right? And had to give some of this back at some point. 3 gig, 4 gig. 4.9, 5 gig.
Computer.
What?
You're gonna break your computer.
We gotta see if we can crash it, right? Yeah, so it's gotten a little bit smarter, so now it's going back down. It's like, oh, you've done a dumb thing, we're gonna limit you. It's harder to crash Windows nowadays because they've gotten a little bit smarter about that. And like, maybe we shouldn't let it do this. So the fine folks who write operating systems who are geniuses, who care about this sort of technical stuff, make sure we don't shoot ourselves in the foot. This used to crash your computer. Right? And that, obviously was probably a bad idea here, but now we'll stop it. So if you don't delete it, it doesn't let it go, even if we just go make a new one. Because C++ is like, oh, you asked for the memory, here you go. And until you give it back, it's not going to let it go. So you got to be careful with these. This is what makes a memory leak. If you allocate memory and don't delete it, it's called leaking memory. You're holding on to something that you don't need. Seems a little funny, like leaking is kind of the wrong term. You think things would get less when you're leaking, but you're getting more somehow. I don't know why it's called a leak, but Chrome is terrible at this. Right? Chrome will just eat your memory all the time here. Yeah.
So why don't you put the delete inside the scope of the for loop?
Yeah, so if we put it in here, then we can make it, delete it, make it, delete it, make it, delete it all the time, and we'll just stay a flat 420 or so, right? Yeah, so if you delete it when you're done with it, it's not going to leak. So this is just showing if you don't delete it, bad stuff happens. And now we don't always do like 100 million integers at a time. That's kind of an extreme example just to make it stress a little bit here. So that's allocating an array of values. Yes, we want to move that delete up above here. So if we put it in here, just make sure we gives the memory back to the operating system. So now when we run here, we'll see it should stay pretty flat as we go here, right? 1, 1, 1, 1, 1, 1. Oh, I only did one, shoot. I wanted like 100 million again. There we go. We're using a bunch of memory here. 1, 1, 1, 1. Uh-oh. Oh, shoot, I did a billion right off the bat. Billion was probably wrong for that. But yeah. So it's not increasing constantly because we're deleting it and allocating, deleting, and allocating it as we go, right? So gotta be a little bit careful that your users don't give you crazy values, but essentially it'll work okay for you here. So we use the delete operator to delete that. The other thing is we have to do that for other pointers as well. So I can make a single allocated pointer using the new keyword if I wanted, without using the array notation to allocate that pointer's memory on the heap rather than the stack. Yeah, accessing it by index is great. Navigating it, sure. Deleting it, good. Did that one. Using null pointer, right? That's our nothing. That's the one that's supposed to be at. So as long as it's not a null, we can keep on going. So that's I. Yeah, that one's fine. Array size, sure. It's not super new for null pointer, but at some point old code didn't have that and they just used 0. But null is from C. You get some really old crazy stuff here as we go. The next thing you can do is you can change the size of an array, but not really. It's sort of a trick we're going to use. So because we know what the size is, what we do is we go make a new one here, and we go add the value. So we're going to make another array, copy the old values into the new values, and then delete the old one, reassign the new one. Because you can't go, so when you ask for an array, a bunch of values, your operating system gives you a contiguous block of memory. Right? You have this much space in order so that this array notation works, right? Because it says, hey, where is the first value here times the size of that whatever you're storing times the index. So the value of values really is just a memory address. It's where is the first one here. So if I were to see out values here and an end line, that's a memory address, right? And if I were to see out the dereferenced value of values, I'd get the first item stored in there. So let's go back and actually put these ones in, and let's do this one. So let's go, hopefully we'll just do like 5, because otherwise that'd be silly here. So let's go enter 5 values. There we go, 1, 2, 3, 4, and 5. This is the memory address stored by the values pointer, which is pointing to a dynamic array. The value stored there is the first value in the array, which is the value 1. Right? Seems a little silly, but that's okay, we can do that. The next thing we can do is I can take my pointer and move around that dynamic array. Now, changing values is probably not what we want to do here. So maybe we want to make another pointer. In pointer, this is my, current value is values. So say, hey, make another pointer, give it the value of values here, right? It's another pointer. Then I can go and loop through and go read those values back out. So I can take my current value and I can add to it, and then I can see out the value pointed at by current value here. And an end line. This is doing pointer arithmetic. This is arithmetic. It's a little awkward here. We're going to just add 1 to the pointer. right? And then go get the next value here. So we'll enter 5 numbers. I just have somebody enter 1, 2, 3, 4, and 5. And we get 2. We took the pointer, right? Started at here, and we said add 1 to it. Well, adding 1 to a memory address, when we know it's an address of an integer, means go add that many bytes that the size of an integer is to that pointer. So I went and added, I think, 4 bytes, right? So we can go and print back out the value of current value, right, before and after. So this is, we'll do current value. We should add some more here. So this is current value of current value. That sounds awful here, I apologize. That's how it does value of current value. This is my pointer. And then value of current value pointer after plus plus, right? We'll see it go up probably by 4 bytes if we did it right. So 5 values, 1, 2, 3, 4, oops, 2, 3, 4, and 5, whatever. So here's the value, and I in an added one, added 4 bytes. So from there, then I got the next value pointed here. I did 2, 3, 4, 5. I got an extra input in here because I'm silly. But you can add to your pointer here to go move where it's pointing. Right? So if you want to, you can go and change the pointer itself rather than say, hey, I want the pointer at a given index. Right? The pointer at an index says, take your pointer, add the index number times the size of what you're storing here. So when I say cout my values at, I don't know, 3 or 2, sure we'll do that here. It says, take the pointer, add the index value times size of what it's storing, right? And then give the value. That is at that memory address. So really it's the same thing as saying, hey, I want to cout values plus, can I just say plus 2? I don't remember if I can say plus 2 or not. We'll see if that actually works for us here. It might work. 5, 1, 2, 3, 4, and 5. There's the memory address. Oh no, what do we get here? Value, yeah, so values plus 2, shoot, that didn't give us the wrong one here. That's the memory address, we didn't dereference it, that's what we didn't do. So I want, what, this dereferenced? Ugh. Reading invalid data, values plus 2, dereferenced. That one might do it. 5 values, 1, 2, 3, 4, and 5. There we go. Now we get out that what we wanted. So when you take that and add something to it, it's adding the size of that value in integer, right, of that in memory, to that memory address. And we said, oh, but then by the way, dereference it because you're a pointer. Give me the thing you're pointed at. So values index of 2 is the same as dereferenced values plus 2. This is how our arrays actually work in memory. Right? That's why you need a contiguous block of memory so that index notation works. You can say, hey, you want the 722nd thing? Okay, take 4 bytes times 722, add it to values. Boom, there's where you need to go look. So you get instant access to all your values in memory there to make things really fast. And one of the things we're going to start looking at is how do we make things fast? Because fast is important, right? Or at least not being slow is important. Maybe not quite as important as being fast, but not being slow is definitely good. So we can do crazy things with pointers here, okay? Oh yeah, copying, right? So you copy, make a new array, copy each value from the old array into the new one. I don't think we need to do this one. Is that okay? Because you got the example here. Appending one array to another, just you have to resize them, right? And then you just add all the values in here. That one's pretty straightforward as well. In an efficient way. So we don't want to have to resize our array every time we add something to it, because that means we have to do n copies, right? If I have 7 things, you don't want to have to copy 7 things to add the 8th thing, and then copy 8 things to add the 9th thing, and then copy 9 things to add the 10th thing. That's going to be very inefficient, right? So what we typically do is we just double in capacity. So we'll say, okay, I might have some variable number of values here in my dynamic array, but I don't want to have to resize every time, and pretend like we don't know about vectors for some reason. Vectors are much better, but that's okay if we want to do this with dynamic memory. So we would allocate double the space that we need here and have extra spaces. We just need to track, hey, where is the next open space, right? So this sleep hours size, right, knows where is my current next space here, right? As we're increasing this, so just make sure we can have room for things as we go. To delete something in an array that has extra space, you just have to shift everything back one, right? You don't want to leave a gap in the middle because then the index notation is going to be really funky. Like, hey, I have something 0 index, 1 index, but remember that index 2 doesn't have anything, go to index 3. Like, that's not going to work, right? So to delete index 2, you just take everything from beyond then and shift it by 1. That's still going to take a bunch of operations, right? You just go through and copy everything back 1. All right, there's their example. The next thing we do with pointers, because that was fun and all, but the next thing we do with pointers is create instances of our classes as pointers, because we want to be getting things stored on the heap, right? We don't have as much room on the stack here. We want to start doing things on the heap. So we're going to start using the new operator when dealing with our classes here. So we can go make a silly class in here. We'll add a little header file, make a little header file, header H, whatever, sure. This will be class. We did shapes. Did we do shapes already? We did chairs. Did we do shapes? No, we didn't do any shapes. So we'll do, how about rectangle? Class for rectangle, we'll have our private section, we'll have our public section. All right, so rectangle then should have an int for, probably an int is fine, for length, and an int for width here. And then it should have a constructor, right? So we're gonna have a rectangle constructor that takes an int for length and an int for width here. And we'll go do something with that in a second. And then we'll probably have a set length and set width. Set length, int length, and a set width takes an int width, and a get length returns this length, and I'm forgetting, these are void set length, void set width, and then an int get length and int get width. There we go. Now those red lines will go away. Get width, return this width. All right, so to set the length, we want to make sure it's valid here. So again, so we can say, hey, if the length is less than 0, we're going to throw an invalid argument. Valid argument. You have to be less than 0 or something like that. I don't know, length can be less than 0. Sure. I gotta use namespace, right? Namespace, standard. Isn't that invalid argument? Am I doing something wrong again? Oh, if we can include our standard exception. Did that happen automatically for me last time? I don't remember doing that. Clicking that button. I don't know, that's fine. Otherwise, we set my this length to the length, and the same with width. We'll just copy paste this, but change it to width here. Width, 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 and width, right? So you can set the widths. Then our constructor should probably use those, right? So we want to call set length and set width, and the length, and call set width to the width here. Great, so now we have a class. We got rectangle. Now we can go and include that. So we're going to include header H, isn't it? Header H file, sure. And then we want to do that maybe up at the top. We can do that up at the top. So before, to make instances here, we had rectangle. We said rectangle, I don't know, small rectangle was, I don't know, 2 by 3. Sure. So this will allocate it on the stack. If we want to allocate this on the heap, here we're going to use a pointer. So I'm going to say, hey, I want a rectangle pointer called big rectangle. And it's going to equal a new rectangle, and we have to call this constructor. So notice there's like 3 things here in the IntelliSense. One constructor is length and width, another constructor is a reference to a rectangle, and another one is a rectangle reference. That one's really awkward here. We'll get to those later. So length and width here. So okay, this one maybe is 5 by 10. So now I've allocated that on the heap, and I have a pointer to wherever that is in memory here. Then if I want to use my big rectangle, right, I can use all these things, but notice I tried to do dot and it changed it on me here, the little arrow notation. So with small rectangle, I can say dot get length here, and I can do something with it. right? Because this is not a pointer, so the dot notation works. With pointers, you have to use arrow notation. I don't know why. I didn't write C++. I apologize here. So we can like see out, I don't know, length of small rectangle is this thing here, and then line. That's a little long for the zoomed in screen, I'm sorry. So we'll bump that down one. And then we'll do the same thing for the big rectangle, length of big rectangle. But now when I say big rectangle dot get length, it changes it to the arrow notation. So when you're using pointers, you have to use arrows. Pointers require arrow notation. Yeah.
Is it similar to when we were in the class and you said this?
Yep. Yeah, exactly. So this is technically a pointer, right? If you hover over it, it says, hey, it's a rectangle pointer. And I don't know if you noticed that in the little IntelliSense here. This is a rectangle pointer here. So we're using the same notation here to go get those values with the this pointer, right? So if we're using pointers, we have to use this arrow notation. We'll get used to it. Thankfully, Visual Studio lets you do dot, and then it just translates it for you, because it's like, hey, yeah, I know what you mean. I got you for that. Then I think that's about it for our pointers here. Let's go make sure that works, right? We should get length. Oh, I put the arrows in the quotes. That's fun. That just looks dumb. Okay. So we get our length back up. So that worked okay for us here. So we can make objects using pointers, using that new keyword to allocate it on the heap here. And then we get our constructor, which is great. Let's see, what else do we want here? Yeah, the arrow notation. The other thing you can do, if you really like the dot notation, you can dereference your pointer, right? So if you want, we can do it again here. You can dereference pointer if you really like dot notation. So I can say, hey, big rectangle, dereference that. Now the pointer doesn't work at all. Now I have to say dot get length, because that makes a lot of sense. But hey, the thing that you're pointed at, give me the thing you're pointed at, now I can use dot notation on the object. If you're a pointer, it's like, oh, hey, this essentially dereferences it for you with the arrow notation. The thing that you're pointed at, call get length, right? So that's what the arrow is. It's the thing that you're pointed at. Go do that thing. That's all with that one here. So you can use that notation if you think it's fun. Let's see, so we got that one. Cool. Deleting it then, right? We want to go delete that pointer when we're done here. So eventually we can go delete our big rectangle, right? Delete big rectangle. It goes and frees up the memory. We dynamically allocated it. We need to free it up, right? We're done with dynamically allocated objects. Free the memory. When your program shuts down, it's going to free it up anyway, but it's a really bad habit to rely on the program closing, because as we get more and more complex with our programs, they stay open longer and they do more things, right? So anytime we're done with an object, we're going to make sure we go free it up, right? So to go delete it here, and then if we see out big rectangle here, we should get something fun, right? This is before delete and after delete, right? When you see out a pointer, you just get a memory address. Here's memory address. Well, that's a different memory address now that we deleted, right? Sure. Right? If you want to be very nice about it here, yeah, it's warning us, hey, using uninitialized memory, right? It doesn't actually point at anything. You went and deleted it here. We could then go take big rectangle and assign it null pointer here. That's maybe a little bit nicer, and it should just be actual 0 here. Yeah, now we get an actual 0, right? Delete just trashes it. I don't know why it starts with this one instead of 0, but sure. Right? So it's a good habit to put them at null pointer, because that's something we check for. Is, hey, if this pointer equals null pointer, it's no good. You've deleted it. It's garbage now. Don't use it anymore. Don't touch it. So it's a good habit to set pointers to null when you're done. Right? Just a good thing to do. And it's like it's going to warn you here. You did weird things. That's all. All right, so we can delete them. Here's we go. The next fun thing, right, is arrays of objects. So what if I want a bunch of my rectangles, right? Well, we can do that. We can say, hey, I want to create an array of those objects, right? So here's a pointer then equals a new array of that object, which is fun. So we can go through and make lots of rectangles, right? So this will be a rectangle pointer, rectangles equals new rectangle, and maybe we'll put 5 in here. Uh-oh. But now it's yelling at us. It says no default constructor exists for class rectangle. If you don't have a no argument constructor or default constructor, it can't go make those objects in memory because it doesn't know how to create them without default values. So one of the things we need to do then, if you want to do that, is you have to have a default constructor. Maybe we'll just use the optional parameters. Have you done that with optional parameters? Say, hey, if you don't give me a value, I'll be 0. These overloads. Okay, so maybe someone's seen it before. That's good. So it lets it be optional, right? So we'll start at 0. That's fine. You can be 0 till you tell me otherwise. But now I can run my code, and I'll make 5 rectangles, all with 0, 0 length and width, right? Then I can go do, so rectangles index of 0 dot get length, right, will be 0. For some reason, we don't use the arrow notation because we've already gotten the value pointed at by this, right? Remember, this was like the same thing as saying, I want the dereferenced rectangles, right? Dot, get length, right? This index notation, wow, what is that? My semicolon, is that all? Yeah, so remember, index of 0 is the same as this plus nothing, plus 0, dereferenced, so that's why we don't use the arrows in the array, because it's kind of automatically dereferencing it here. This is sort of stuff that's super confusing and why everyone hates C++, but that's okay. We'll get it eventually. It's not a big deal here, right? So we could see out length of rectangle index 0. Goodness, that side. I can't type today. We'll do that same one here. And maybe we'll add an end line. And another end line. So we made them, they should all be 0, right? Because we didn't set anything yet. Right? So either notation is going to work for you here, whichever one you want to do with this. Right? So we made that array, right? When you're done with it, go delete it. Go delete your array of it here. The next fun thing we can do is our classes can use dynamically allocated data. And that's what we're going to do for our project. Right? Our class will have a class that has a dynamic array of something else. So we're using dynamic memory everywhere. It starts to be a little crazy here. So the pointer holds the dynamically allocated array's address. Right? We need to know how much we have in there, and then we need to know the size currently held, because we want to oversize it, right? If this is the kind of thing we're going to add and subtract from as we go. So in this case, they've got this activity here, right? And that activity then has a pointer to the activities itself. So your activity tracker has a bunch of activities that you've tracked. So it's going to dynamically allocate some number of locations for this number of activities we're going to track. Hey, okay, I did this exercise for this amount of time, this exercise for this amount of time. I want to go add and subtract from it, right? So we get these great little, did you do UML at all in 150? I know I barely touched it because I think it's dumb, but it's not dumb. It's really useful here. So it gives you a little picture of a class, and it's a very common format here. So the top line is the name of the class, the middle line are its attributes, and the bottom section are all of its functions. Plus means public, minus means private. Right? So we see the private attributes, we see public functions, private functions, and it just gives you something you can show somebody to give them a picture of the class without all the details. It's super helpful. I don't mean to trash it. It's very useful. I didn't use it a lot in industry, but it's a very common tool. Some companies really like having UML documentation. Other people think it's kind of silly, like some of us do, but that's okay. So this is just a picture of what that looks like, right? It's just describing what that class will be, and then depending on the tools you want, big companies like IBM sell really fancy tools that if you give it UML will generate code for you. Again, gets and sets are pretty basic. They're really easy to generate. Anything hard, it doesn't generate well. I mean, our chatbots can generate some stuff here, but you got to be a little careful with it, right? So the idea was if we design it in UML, designers can do it, and then it'll generate code for you that's garbage code. And they're like, hey, yay, we've got good code. But it never really panned out, so it didn't get widely adopted. But go learn all about that in your software engineering tools class. That's some fun stuff. So dynamically allocating the memory then said, hey, I want to allocate a new array of that size. We're going to start with this many here, and we can go double when we need to. We can go double when we need to. So going through and doing this, like following this example, will help a lot with the next project, because that's a similar thing what we're going to do with this. The last piece we have to get to, I don't think we've got, is this, our constructors here. We're not quite there yet. So if our classes are using dynamic memory, we have to do a couple things, because we want to make sure that we can take care of the things that we need to do. So rectangle's not a good class for that. I'll probably end up putting that in the video for next week, or for Thursday. So I'll have the video where we look at how a class should dynamically allocate memory. And if we're dynamically allocating memory, we need to make sure that we can delete our class. So we've written constructors before, right? The constructor is this. You write something called a destructor that says, hey, when you call delete on this object, what happens? So if this class goes and allocates memory, and we never call delete on the thing that this class did, that memory is leaking, right? We're never going to get rid of it. So the destructor says, when you delete this object, go run this code, and in that code, we'll go delete the dynamically allocated memory that that class created, right? Then we have to figure out how to copy them, right? So if I want a copy of a class here, if I just make a copy of its attributes and you have a pointer attribute, the value of that pointer is that location in memory. So if I make two, rectangles are probably a bad example here, but if we made two activity trackers, right, using their example here, our activity trackers, right? The value of activities is the memory address of where that array starts. So if you make a copy of it and you say, okay, hey, you've got this many capacity, this much size, and here's your pointer, you now have two pointers pointed at the same memory location. That's not actually a copy. We call that a shallow copy. And so if you change one, you've changed them both, essentially. Remember, we changed numbers, we changed the number pointer, another number pointer. They were both pointed at the same thing. So one of the things we can do is we can write code to let you copy objects and allocate new memory to copy them, right? So it makes a new array, copies items from that array into the new array, right? To actually make a new instance so you have a new dynamic array. So we'll look at that on Thursday as well. All right, so let me show you the project here. So we go add this one in for project 0. So we'll get 2 weeks to work on this one here. So this is our new project 0. Project 0 here. This is classes, pointers, and dynamic memory. Look at that. I love that type ahead. It remembers. How smart is that? And I'm going to go shamelessly copy paste because I already did this last time. Right, is that okay? Shameless copy paste. Okay, you guys aren't too embarrassed for me. Thank you. So again, submit the URL to your repository, add a README file with the output of your program. So we're going to write two classes here. We're going to have a class for trainer. Trainer has some information. So trainer has a name, it has a level, it has a number of experience points, it has a max number of fighting pets, and it has a dynamic array of type fighting pet. So your trainer will have some number of fighting pets here, right? We're going to include that destructor, and we'll talk about the copy constructor, copy assignment operator, how we make copies of it, handling dynamic memory. We'll do that in the video Thursday for you for the trainer class. We need public methods for set and get name, right? You can set your name, you can get your name. We'll have methods for set and get max number of fighting pets, right? We'll have get methods for level and experience points, so you can't change these things directly here, right? There's no set to change them, right? This is some process will go change them, right? If it's not appropriate to directly change it, we don't write code for it, right? And then we have a method for add experience points. If your experience points goes higher than the level times 1,000, you increase your level and reset your points to 0. And so as you add experience and you're level 5 times 1,000, if you have more than 5,000 experience points, you now go up to level 6. Congratulations, trainer, level up, right? And then you go back to 0. We're gonna have a method for add fighting pet. Add the fighting pet to your dynamic array of fighting pets in the next open slot, right? Because we have some number of slots here in the dynamic array. Now, in our case, we're not going to double because that's a lot of work here. We don't want to bother with that. So we're just going to raise an exception if you have no more slots. Hey, when we created this, you had room for 5 fighting pets. You've added 5. You get no more. You're out of room for fighting pets, right? Those little balls don't fit in your pocket anymore. Fighting pet balls, definitely not ripped off of any sort of other game out there or show out there. And then we're going to add a method for add more fighting pet storage. So if we want to make more storage, this sort of thing probably happens with level ups, but again, don't worry about it right now. Like nothing has to happen automatically. Then we'll go make that array probably double the size, or whatever it happens to be, whatever that larger size should be. We can come up with it later. We copy the fighting pets into the new array and make sure we delete that previous array. Don't let any memory leak here. Okay? Fighting pets are just name, number, and combat power, and add sets and gets and a constructor and whatever else you want for that one here. They're not very exciting, but we have a dynamic array of those things here, right? So this is projects group here. So you're going to turn in the website URL for me here. So this is whatever you come up with. I'm not asking for you to actually add logic for people to play any sort of game with it. We're just writing the classes for it here. But you want to make sure your code works, right? Any code worth writing is worth testing. Make sure it works. So try something and make sure all these things work here. Whatever you got, go for it. Turn in what you got here, okay? So this one will be 10 points. Again, the points only matter within the projects category. Next project will probably be worth like 15. The one after that's like 20, as we get to build on all these things and do more and more and more stuff here as we go. But this one gets us started, okay? So this will be due 2 weeks from today. So that's the 4th at 3:30 p.m. All right, I'll use the dropdown, sure. So 3:30 p.m. So the first thing I'll do in class 2 weeks from now is I'll go over my solution to the project. I'll show you how I would go and do it. Again, it'll probably take me not too long to do it, but I've been doing this for 20 years, so don't feel bad. It's supposed to take you a while, right? If this takes you half an hour, I didn't give you a hard enough project, right? Let's be honest, right? The minimum federal guideline is 2 hours of work outside for every credit inside. You're supposed to have 8 hours a week of homework, right? Across the 2 weeks, plus the labs, ideally we get done in person, but those sorts of things here. So it's supposed to take a while. If it's taking you more than 8 hours, reach out to me, please. Hopefully sooner than that, right? Like if you're stuck on something, give it a good half hour to hour trying to solve it yourself, right? That's good problem solving skills here. Bang your head against the wall, whatever you have to do. But after about an hour, reach out to me. Most of the time I can get you unstuck in 5 minutes or less. You're like, oh, hey, maybe you missed the star here. Maybe you're doing the wrong thing here. Whatever it happened to be, I'll get you unstuck here. Okay? All right, so we got that to work on. We got lab tonight at 6. We'll be working on classes and exceptions. And then next week's lab, we'll do some more with pointer practice and things. Is that okay? I don't want to jam too much into lab tonight. We got a little bit of time to work on it because we got 2 weeks for this one. Okay? All right, awesome. I'll see you over in the HPEC building in a little while. Maybe we can get some nice cold dinner from the cafe because they close the hot food. Drives me crazy.
When was the lab?